Hello and welcome to another review session for Calculus 3208 as you prepare for your final exam. We're still in the topic of derivatives here, but we're nearing the end. We're getting into implicit relations, and with implicit relations next will come implicit differentiation and then some quick applications of that before we jump into the next unit. So with this session today, we're just going to talk not about implicit differentiation, we're just going to talk about what implicit relations are to get a better understanding of all of that before we get into why we have to take their derivatives, etc. So we're going to highlight a few important things here that refer to implicit functions. So first of all, we want to talk about explicit versus implicit representations. So we're going to talk about what that means to be an explicit representation versus an implicit representation, when we can have both and when we can't. And then when we can have both, we'll talk about taking a function or a relation, I should say, that's been represented implicitly, and then rewriting it and talking about how to represent it explicitly. And then we'll talk about some relations that we cannot write explicitly or not very easily anyway, so some that we can't really get there with. And then last but not least, some of the work that we'll actually do with this will be computing some values for x and y coordinates with implicit relations, and how we have to be careful, because often with implicit functions there's more than one place to get for y for one particular value of x, because with this relation business we know we don't have to follow the rules of functions anymore, so we can have two different outputs for one single input, which is a bit of a strange thing because we're so used to thinking in terms of functions. Alright, let's get started. So the first thing we want to talk about is explicit and implicit relations and what they are. So an explicit relation, or an equation that we write explicitly, is when we represent one of our variables in terms of just the other variable. And I know that sounds a little bit like it should be obvious, but we think about this. Look on the left side of this equation here in the first one. We only have a y, nothing else. It's all by itself, and there's no y's over here. It's just operations on the x variable on the other side of the equation. And that's the way that we typically are used to seeing functions. But not all relations are functions, just like not all rectangles are squares. So we got to take a look outside the box a little bit here. Haha. So we can also represent relations implicitly, which can be any equation at all that relates x and y and doesn't necessarily have to have one of our variables isolated. So for instance, this really ugly looking equation that we have down here would be a very big challenge to try and get y by itself, for instance, to isolate the y variable and write this explicitly. In fact, I'm not even sure it would be possible. But the idea being that sometimes because we can't do that, we have to deal with relations that, or relationships between two variables that are represented strictly as an implicit representation. Okay, so let's take a look at some specifics. So one of the most common implicit relations that we're used to dealing with is the equation of a circle. So a circle, we should know from our 3200 course that we did, is by Pythagorean identity we come up with the idea that x squared plus y squared equals the radius squared. So this particular circle I'm talking about here, x squared plus y squared equals 25, would just be a circle with its center at the origin and with a radius of 5 units. So you can look over here on the right that we actually have a graph of that circle that's represented here. Well, is it possible for us to take the equation that we have representing that circle and write it as an explicit function? Well, we could sort of try. You can think of the algebra that would be involved with that. We'd of course want to take y squared and get it by itself first. And then we'd want to get y by itself by probably taking the square root of this stuff. But we almost have to define that piecewise to say that it's plus or minus the square root of 25 minus x squared, because there's two different halves to that. So we have to be careful about how we represent that kind of stuff. So what we've done down here below that is we've kind of broken things down to make them a little bit nicer. Okay, so hopefully everyone remembers from their grade 10 course that they did many, many moons ago, that if we want to check to see if something is a function, we can use this vertical line test. And basically what the vertical line test says is if I can draw a vertical line anywhere on the graph, and that vertical line intersects my curve in more than one place at a time, or at more than one point, then what I have is a relation that is not a function. And if I, for instance, draw a vertical line up here on my circle graph, we can see that the graph of a circle is not a function, and that's going to be true at lots of different places. If I grab that picture and I drag it around to other spots, I get the same problem. This is not a function at all, okay? So when we have these things that are not functions, sometimes representing them explicitly comes with its headaches, as we just saw algebraically. So down here, we can see that when we write out this plus or minus 25 minus x squared in two different ways, we split that up and talk about how that actually represents two different things. We look at the first one, and it's just sort of the top half of the circle. The second one is the bottom half of the circle. So we actually have to split this into two different definitions, or two different functions. So two different simultaneous functions to really represent the one relation. Okay? So can we represent it explicitly? Sort of. Not really, but sort of. All right. So let's move along. So the circle is an example of a relation that we can sort of represent explicitly, but there are some that we cannot, or at least not with any degree of facility. So for instance, here we're going to talk about a curve called Descartes' folium. So this was something that René Descartes came up with many years ago, famous French mathematician. What René Descartes said was that if I take x cubed plus y cubed equals 6xy, it gives me the picture of a really neat looking curve, kind of a famous one in the math world, and it looks like this, and that's called Descartes' folium. Kind of looks like a ribbon or a piece of string that you're tying in a loop or something. But let's say I wanted to represent that as an explicit relation. Well, if I want to represent that as an explicit relation, and I think about the graph of the function that I have, in some sections, for instance, right around these values of x, I can get up to 3 different values for y for one single value of x for that. So barring restricting domains to throw certain pieces of that out, how do I deal with that? Well, if I wanted to write it explicitly, I'd have to actually write 3 different functions. So here's the first one, here's the second one, and here's the third one in terms of their graphs, because of the 3 different possibilities that I could have there. So what are those functions? Well, I don't think I know of anyone who could do the algebra on that by hand. Apparently it can be done by computer algebra systems, but the functions that you actually get out of it are really very complicated. But what we want to understand about them is basically they're just functions that are dependent on this variable y. So y is our dependent variable, and if I think of y as being a function of x, I can just rewrite my equation this way. So I've got f of x all cubed here, and 6x times f of x instead of times y. So basically the 3 different functions that I would have to use to represent these 3 graphs over here would have to be functions that satisfy this particular equation. So that's one of my favorite topics in math, is functional equations, and that's what that actually deals with. So what does any of this stuff have to do with our calculus that we're trying to get into? Well, let's look at some examples. Let's see if we can express this particular relation explicitly. And it says using a piecewise function, but it's not really a piecewise function. It's just kind of a function that's defined in 2 different ways, okay? So I did get this question from another resource, but I'm not really keen on using that word piecewise with this, but we'll talk about why in a sec. Okay, so let's say I wanted to rewrite this so I had y by itself. So I'd take 2y squared equals 6 minus 3x squared. Very similar algebra to what we did with our circular function earlier. So this gives us 6 minus 3x squared all over 2. And so y would have to be equal to plus or minus the square root, and square roots often give us headaches, don't they, of 6 minus 3x squared all over 2. So there's our function if we write it out with a plus or minus notation. But basically what this means is that if I were to write this explicitly, I'd have to have 2 different possibilities here. The first one would have to be the square root of 6 minus 3x squared over 2, and the second one would be the negative square root of 6 minus 3x squared over 2. And I'd have to express this. It can't be written as one function because that is not a function. The graph of this, by the way, is actually something called an ellipse. which we don't really cover in high school anymore, but we used to. Anyway, so if we look at this, we'd have to split it into two pieces and talk about how those two functions simultaneously would give us the one function that we're, or the one relation that we're interested in. So if we wanted to, let's say, take a derivative of this function, getting back to our calculus stuff now, I could rewrite this explicitly like so, and then look at the two different parts. So I could say maybe f of x equals this one, and then we could say g of x equals this one. And then we could take the derivatives of each of those, or we could take the derivative of the y equals the plus or minus bit, keeping in mind that it's really two different things going on. And we could look at the derivatives of those explicitly. Okay, so sometimes that's actually a possibility for us if we do have to find a derivative or deal with rates of change in a relationship like this, where it's not really explicitly written to start with. But there are some cases when we can't do that. And so what would we do if we had to take the derivative of such a function? And that's why we're looking at these implicit relations, is because they give us an idea for how we would deal with this. So let's say I had this particular relation, which is kind of icky, and it says I want to find that it says that two lines are tangent to this curve and defined by that relation when x equals 2. We have two different tangent lines. How can you have two different tangent lines? Aren't they supposed to be unique? Well, if you'll forgive me for backing up a couple of slides here. For instance, if we come back here to the folium of Descartes, and I said maybe x equals 1 is a point right here, you can see because I've got three different sections of my curve that I could have three different tangent lines in three different places, right? So that's basically all that's saying. At any one of those points, I'd only get one unique tangent, but I could actually have my tangent lines at three different points here. So two lines are tangent to this curve when x equals 2. So it says find the y-coordinate of both points, and perhaps be more specific, I should say here, both points of tangency. So we got to find the y-coordinates of both points of tangency when x equals 2. Well, it's only an exercise in algebra now. So if I let x equal 2 in that equation, I have 2y squared is minus 7. Oh, sorry. Let me rewrite that for you because I shouldn't let that be so messy there. So let's try that again. So we're going to have, when x equals 2, it'll become 2y squared minus 7 halves of 2y equals negative 6. Okay? So 2y squared, and multiplying negative 7 over 2 by 2y, I'll just throw those 2's away, minus 7y equals negative 6, or writing this as a quadratic, 2y squared minus 7y plus 6 equals 0. Aha! So now we can see why I'm going to get two different y values for that one particular value of x. This is quadratic, and we can factor that, of course. So we'll have factors that start with 2y and y. And I need two factors of positive 6 that will make this work out for me. So I'm going to guess that those two different factors for positive 6 here are probably going to be, oh, we've got to add up to a negative 7, don't we, in the middle. So let's go with, how about a negative and a negative? And we'll make one of them a 2, and we'll make one of them a 3, so that 2 times the negative 2 would give us a negative 4, and 3 times 1 would give us negative 3. So that works out. All right, so if that's the case, our zero product property should tell us y could be 3 over 2, or y could be 2. So basically, off the top of my head, I have no idea what this graph looks like, but I know that if x equals 2, then I've got two different values for y. So if I wanted to find the equation of a tangent line there, I'd actually have to have two different tangent lines, unless I was specifically told which one to look at. All right, so here's the your turn question, very similar to what we just did. It says if f of x plus x squared times f of x squared equals negative 20, then find all possible values of f of 1. In other words, when x equals 1, what are all the values of the function f of x that you could have? So give that a whirl. I'll jump over to the solution now. So here's the solution for that. We fill it in, and once again, it's a quadratic that we solve. So we get two different y values, or two different values for f of 1. One of them's at negative 5, and one's at positive 4. Okay, so let's run down the key ideas we talked about. It says an explicit relation is algebraically represented with the dependent variable isolated, And an implicit relation is algebraically represented, oh, I can't even speak today, represented without isolating the dependent variable. So the equations representing some implicit relations can be rearranged, as we saw, like the circular one, to isolate the dependent variable, while for some it is best, or at least much less complicated, to leave it represented implicitly only. And that actually makes our lives a lot easier. And we can determine values of the variables in an implicit relation if given values of the other variable, if we just sort of use some basic equation solving techniques, like the quadratics that we saw. Okay? So that's a bit of a rundown about what implicit functions or implicit relations are versus explicit functions. And in our next couple of sessions, we'll talk about how we deal with the calculus of them. Okay, thanks. Good luck studying. Hope that helped.